Introduction.
Aditya, did you see my specs? I'm not able to see anything without them.
Yes, Grandpa. Here they are.
Now I can see. So how are you today?
I'm good, Grandpa. I want to ask you something.
Sure, ask me.
How do the specs help you to see clearly?
Actually, in the specs, the lenses are fitted with correct measurements. And with the help of them, I can see this beautiful world.
Can you tell me more of it?
Sure. Come with me. I'll tell you more about lenses in our new chapter, Ray Optics and Optical Instruments.
Objectives. At the end of this lesson, you will be able to explain refraction at spherical surfaces, use lens maker's formula, find the position of image using thin lens formula, explain refraction through prism, explain dispersion by a prism, explain the working of human eye, explain the working of microscope, explain the working of telescope. Refraction at spherical surfaces and by lenses. Refraction at a spherical surface. The figure given shows a convex refracting surface separating two media. Let P be the pole and C the center of curvature of the refracting surface. Let N1 and N2 be the refractive indices of rarer and denser media respectively. Let O be a luminous point object on the principal axis of the convex refracting surface. An incident ray OA after refraction at the point A on the surface bends towards the normal NAC and goes along AI. Another ray OP falls normally on the surface and proceeds undeviated after refraction. The two refracted rays meet at I, which is the real image of point object O. The relation between object and image distance in terms of refractive indices of the medium and the radius of curvature of the curved spherical surface is N2 by V minus N1 by U is equal to N2 minus N1 by R. Refraction by a lens. Suppose L is a thin lens. The refractive index of the material of lens is N2 and it is placed in a medium of refractive index N1. The optical center of lens is C and x-x is principal axis. The radii of curvature of the surfaces of the lens are R1 and R2 and their poles are P1 and P2. The thickness of lens is T, which is very small. O is a point object on the principal axis of the lens. The distance of O from pole P1 is U. The first refracting surface forms the image of O at I' at a distance V' from P1. The image I' acts as a virtual object for second surface, and after refraction at second surface, the final image is formed at I. The formula of refraction for thin lens is, this formula is called lens maker's formula. This formula also holds for concave lens. If the first medium is air and refractive index of material of lens be N, then N2 upon N1 is equal to N. And we know that. So the lens maker's formula can be written as, this is called thin lens formula. The focus on the side of the source of light is called the first focal point, whereas the other is called the second focal point. Magnification M for the lens is defined as the ratio of the size of the image to the size of the object. M is equal to H' by H is equal to V by U. Example. A 6 cm high object is placed at a distance of 30 cm in front of a concave lens of focal length 15 cm. Calculate the position of the image. Solution. Given u is equal to minus 30 centimeters, f is equal to minus 15 centimeters. Hence, from lens formula, 1 upon f is equal to 1 upon v minus 1 upon u. We have 1 upon v is equal to 1 upon f plus 1 upon u is equal to 1 upon minus 15 within parentheses plus 1 upon minus 30 within parentheses is equal to minus 1 upon 15 minus 1 upon 30 is equal to minus 3 upon 30, or v is equal to minus 30 upon 3 is equal to minus 10 centimeters. That is, the image will be formed on the side of the object at a distance of 10 centimeters from the lens. Power of a lens. The power of a lens is measured by its ability to deviate the rays towards the principal axis. The lens L2 has focal length less than L1. Therefore, lens L2 bends the rays more than L1. Hence, the power of the lens L2 is greater than that of L1. Clearly, P is directly proportional to 1 by F. In SI system, the focal length is in meter. The power of the lens is in diopter. Therefore, P is equal to 1 by F in meter, diopter D. Clearly, the power of a lens of focal length 1 meter is 1 diopter. Combination of thin lenses in contact. Suppose two thin convex lenses L1 and L2 are placed in contact in such a way that they have the same common axis. The focal lengths of lenses are f1 and f2 respectively, and the medium is same on both sides of lenses. O is a point object on the principal axis at a distance u from the first lens, L1. The lens L1 deviates the rays towards I. That is, I is the image formed by the first lens, L1 alone. If V' is the distance of image I' from the lens L1, then for lens L1, 1 by V' minus 1 by U is equal to 1 by F1, name it as equation 1. For lens 2, 1 by V minus 1 by V' is equal to 1 by F2, name it as equation 2. Add equation 1 and 2 and we get 1 by V minus 1 by U is equal to 1 by F, where 1 by F is equal to 1 by F1 plus 1 by F2. If the number of thin lenses are in contact of focal length F1, F2, F3, then the effective focal length of their combination is 1 by F is equal to 1 by F1 plus 1 by F2 plus 1 by F3 and so on. In terms of power, P is equal to P1 plus P2 plus P3 and so on. The total magnification M of the combination is a product of magnification M1, M2, M3 and so on of individual lenses. M is equal to M1, M2, M3. Refraction through a prism. A prism is a homogeneous, transparent medium enclosed by 3 vertical plane surfaces. 2 of these surfaces are usually polished and are called refracting surfaces, and the angle between them is called the angle of prism or refracting angle. The third surface, known as base, is usually grounded and does not allow the transmission of light. Let us consider the passage of a monochromatic light ray PQ through the glass prism ABC. At surface AB, when ray enters the glass at angle of incidence I, it bends towards the normal at Q at angle of refraction R1 and strikes the surface AC at R. The angle of incidence at surface AC is R2 and the ray emerges into air, making an angle E with the normal R. The emergent ray RS and the direction of the incident ray PQ is called the angle of deviation delta. The angle of deviation delta can be evaluated to delta is equal to I plus E minus A. For a given prism, A is fixed, angle of deviation delta depends on angle of incidence. As the angle of incidence is increased from very small volume, the angle of deviation first decreases, reaches a minimum and then increases. For the minimum deviation, I is equal to E, which implies R1 is equal to R2. Delta minimum is equal to 2I minus A. The refractive index of the material of the prism, N, is equal to sine of A plus delta minimum by 2 divided by sine of A by 2. Dispersion by a prism. The splitting of white light into constituent colors is called dispersion. The component of colors appear in the sequence are violet, indigo, blue, green, yellow, orange, and red. The angle of deviation for violet light will be maximum, and for red light it will be minimum. Therefore, when a white light enters a prism, then the rays of different colors are refracted in different directions, and so they emerge from prism in different directions. Newton's classic experiment on dispersion of white light. The experiment performed by Sir Isaac Newton had put another prism, P2, in front of a prism P1, but inverted in position, and the emergent beam from the prism P1 on the prism P2 and the emergent beam from the prism P2 is a white light. Some natural phenomena due to sunlight. The rainbow. It is an example of dispersion of sunlight by the raindrops suspended in the atmosphere of the earth. This phenomenon arises due to combination of refraction and internal, not total reflection by spherical water droplets. Primary rainbow. When sunlight falls on raindrops, the different rays suffer different angles of deviation. Primary rainbow is formed when a ray undergoes 2 refractions and 1 internal reflection. The intensity is maximum for red rays at 42 degrees and violet rays at 40 degrees. Secondary rainbow. Secondary rainbow. When the sunlight falls on raindrops such that there are 2 refraction and 2 internal reflections, then secondary rainbow is also seen along with the primary rainbow. In this second rainbow, the violet color is deviated more than the red color. Scattering of light. When ordinary sunlight passes through atmosphere containing extremely small air molecules, dust and smoke particles, etc., it is deflected from its path due to interaction of electric field vector of light wave and the target particle. This phenomenon is called scattering, and the deflected light is called the scattered light. Rayleigh law of scattering. Rayleigh law of scattering. The intensity of light scattered from fine particles, dimensions wavelength of light, is inversely proportional to 4th power of wavelength of light, that is, why we see a blue sky most of the time. Sunlight reaches the Earth's atmosphere and is scattered in all directions by all the gases and particles in the air. But light is scattered in all directions by the tiny molecules of air and the Earth's atmosphere. Blue is scattered more than other colors because it travels a shorter waves. This is why we see a blue sky most of the time. Why the sun appears reddish at sunrise or sunset? As the sun gets lower in the sky, its light is passing through more of the atmosphere to reach you. Even more of the blue light is scattered, allowing the reds to pass straight through your eyes. Optical instrument, the eye. Our eye acts as a convex lens fixed in its place through muscles. This lens is called eye lens. The rays coming from a luminous body fall on eye lens and after refraction through it are focused on the retina. Thus, real, diminished and inverted image of the object is formed on the retina. Our mind feels this image erect. Power of accommodation of eye. On account of elasticity of muscles, the eye lens has the ability to change its focal length, which enables us to see near and distant objects. The power of eye lens is called the power of accommodation. The maximum distance at which an object placed can be seen distinctly by the eye is infinity. When the object is at infinity or very far from the eye, the parallel rays starting from it and after refraction through eye lens are focused on the retina and the object is clearly seen. In this state, there is no tension in muscles, that is, the eye is in relaxed state and the focal length of eye lens is maximum. When the object is near the eye lens, the muscles contract to increase the curvature or decrease the radius of curvature of the refracting surfaces of the lens. This causes decrease in focal length of the lens and again a clear message is formed on the retina. Thus the eye can clearly see the near and distant objects. The minimum distance up to which the eye can see clearly by exerting maximum pressure on muscles is called the least distance of distant vision. For normal eye, this distance is 25 centimeters and is denoted by D. For normal eye, the near point D is 25 centimeters and far point is infinity. Optical instrument, the eye. Pupil. The function of pupil is to control the quantity of light entering the eye. When light is strong, the pupil automatically contracts, and when light is weak, the pupil automatically dilates. This process is called adaptation. Persistence of vision. When an object is viewed by the eye, the impression produced on the retina does not disappear immediately after the object is removed from the front of eye. This impression persists for a short time, about 1/10 seconds. This is called the persistence of vision. The point where the optic nerve enters the eye is insensitive to light and is therefore known as blind spot. Defects of eye. Myopia or short-sightedness. Myopia is the defect of eye in which a person can see only nearer objects but fails to see farther objects distinctly. This defect is due to 1. Decrease in focal length of the eye lens. 2. Spreading of eye sphere. Remedy. To eliminate this defect, a concave lens of suitable focal length is used. Long-sightedness or hypermetropia. Hypermetropia is the defect of eye in which a person can see only farther objects but fails to see nearer objects distinctly. This defect is due to 1. Increase in focal length of eye lens. 2. Contraction of eye sphere. Remedy. To eliminate this defect, a convex lens of suitable focal length is used. Defects of eye. Presbyopia. In high growing age, the eye lens loses its flexibility of changing focal length. Consequently, the near point of eye is displaced farther and far point of eye is displaced nearer, so that the eye becomes unable to see nearer as well as farther object. This defect of eye is called presbyopia. This defect may be eliminated by using bifocal lenses. Astigmatism. The defect of eye in which horizontal and vertical objects at the same distance are not focused at the retina clearly is called astigmatism. The astigmatism is corrected by using cylindrical lens. The microscope. A microscope is a device to see nearer very small objects clearly. A simple microscope consists of a convex lens of small focal length. The principle of simple microscope is that if an object is placed between the lens and its first principal focus, the image formed by the lens is erect and magnified. Magnifying power of a microscope. M is equal to D into 1 by F1 by V. When final image is at a distance of distinct vision, that is V is equal to D, then M is equal to 1 plus D by F. When the final image is formed at infinity, then V is equal to infinity. M is equal to D into 1 by F, 1 by infinity, D by F. Compound microscope. It consists of long cylindrical tube containing at one end a convex lens of small aperture and small focal length. This is called the objective lens O. At the other end of the tube, another coaxial smaller and wide tube is fitted, which carries a convex lens E at its outer end. This lens is towards the eye and is called the eyepiece. The focal length and aperture of eyepiece are somewhat larger than those of objective lens. Cross wires are mounted at a definite distance before the eyepiece. The entire tube can be moved forward and backward by the rack and pinion arrangement. Magnifying power of a compound microscope. M is equal to minus V0 upon U0 into D upon Fe plus D upon Ve. Signs here already have been put. Telescope. The astronomical refracting telescope consists of an objective lens system and an eyepiece. However, the two instruments differ in that the objective of telescope has a large focal length and a much larger aperture. Light from the distant object enters the objective and a real image is formed within the tube. The eyepiece, used as a simple magnifier, leaves the final image inverted. When the final image is formed at infinity, the objective lens O collects parallel rays from the distant object. So, an image I is formed at the principal focus FO of the objective. Since the final image is at infinity, therefore, I must be at the principal focus FE of the eyepiece. Thus, FE and FO are at the same place. Magnifying power of a telescope in normal adjustment is the ratio of the angle subtended by the image at the eye as seen through the telescope to the angle subtended by the object as seen directly when both the object and the image are at infinity. The angular magnification is M is equal to minus FO by FE, where FO is the focal length of objective, FE is the focal length of the eyepiece. Did you know? Newton demonstrates that a prism could decompose white light into a spectrum of colors. Hubble Space Telescope helps find the most distant galaxies. Summary. Let us summarize what we have learned. The relation between object and image distance in terms of refractive indices of the medium and the radius of curvature of the curved spherical surface is n2 by v minus n1 by u is equal to n2 minus n1 by r. Lensmaker's formula is this. Thin lens formula is this. Magnification m of the lens, m is equal to v upon u. Power of a lens, P is equal to 1 upon f in meters, diopter d. The combined power of thin lenses with power P1, P2, P3 is P is equal to P1 plus P2 plus P3 and so on. The refractive index of the material of the prism, n is equal to sine of A plus delta minimum by 2 divided by sine of A by 2, where A is the angle of prism and delta m is the minimum deviation. The splitting of white light into constituent colors is called the dispersion. The intensity of light scattered from fine particles, dimensions wavelength of light, is inversely proportional to fourth power of wavelength of light, that is, I directly proportional to 1 upon lambda raised to the power 4. Defects of vision are myopia, hypermetropia, presbyopia, and astigmatism. Magnifying power of a microscope, m is equal to d into 1 upon f, 1 upon v. Magnifying power of a compound microscope, m is equal to minus v0 upon u0 into d upon fe plus d upon ve. The angular magnification of telescope is m is equal to minus fo upon fe, where fo is the focal length of objective and fe is the focal length of the eyepiece.